Hi, this is Barrett Givens, and in this video, we're going to introduce the interior and closure of a set. So the definition is here. Let's say you have a subset A of a topological space X. The interior of A, which we sometimes write int of A, or a little A with a halo on it, okay, is the union of all open subsets of A. So the interior of A is the union of all open subsets of A. And the closure of A, which is written as CL of A, or A with a bar over it, is the intersection of all closed subsets containing A. You want to be careful because in some books they use A with a bar over it to mean complement instead of closure. And so whatever source you're reading or video you're watching, you want to make sure to be clear about what notation they're using. But these are the ones that I typically use and the ones that many textbooks use. All right. So let's kind of go through some facts about interior and closure. So first of all, the interior of A is always an open set and the closure of A is always a closed set. Why would that be? Well, the interior A is a union of open subsets. It's a union of open subsets. So it's a union of open sets, right? A union of open sets. And we know that when you have a bunch of open sets and we form their union, it's still open. So because it's a union of open sets, that tells you why the interior is open. And then similarly, the closure is an intersection of closed sets. And we have a theorem that says whenever you take an intersection of closed sets, it's closed. So the closure of A has to be closed. Okay. The next fact is that the interior of A is a subset of A, and the closure of A is a superset of A. All right. Why would that be true? Well, the interior of A is a union of subsets of A. So every element in that union is a subset of A. So if you take a bunch of things that are all completely contained inside of A, even when you union them all together, you're still going to be inside of A. So it's because they're all subsets that we're unioning over. That's why the interior continues to be a subset. And then similarly on the right, the closure is an intersection of closed sets containing A. So every set that I'm intersecting here already has A inside of it as a subset. So even when I intersect all of them, I'm still preserving that subset property. Okay, so the interior of A is an open set inside of A, and the closure of A is a closed set surrounding A. Now we can also say that A is open if and only if A is equal to its own interior. And A is closed if and only if A is open to its own closure. Okay? So why would those facts be? Well, let's look at A being open if only if A is equal to the interior of A. First of all, if A equals the interior of A, we already know from the first fact above that the interior of A is open. So if I say that A is equal to the interior of A, then that means A is equal to a set which I know is open. So then obviously A would be open. Okay, if A equals an open set, then A is open. What about the other direction? Suppose I start by assuming A is open. Well, then when I union all of these subsets, one of the sets I'd be included in the union is A itself. It would be one of these open subsets of A. So if A were open, then when I form this union of all of the open subsets, one of the sets involved would be A itself. And so I'm going to be doing A unioned with other things that are smaller than A. That'll give me A. So when I form this union of open subsets, I will get A. Okay? A similar argument can work to show that A is closed if and only if A is equal to the closure of A. Um, so now that actually helps us kind of think about the sort of intuitive meaning of interior and closure. Intuitively, the interior of A is the largest open set contained in A. And the closure of A is the smallest closed set containing A. So the interior is what you get when you start from the inside and you go as big as you can while still staying inside of A and staying open. So the interior of A is what can you get inside of A that's as large as possible and open. And then the closure of A comes the other way. You take closed sets and you kind of shrink down to A. So the closure of A is if you think about all possible closed sets, what's the smallest one that contains A? Okay. So one more fact, I think. is that if A is a subset of B, then the interior of A is a subset of the interior of B, and the closure of A is a subset of the closure of B. All right. So let's just really quickly kind of visualize what's going on here. So if I have a set A, interior of A is sort of like how close can I possibly get inside of A? So the interior of A is the open set that's inside of A that is as large as possible. And the closure of A is sort of what I have on the outside. Closure of A is what I get on the outside. I don't know why I'm drawing it this way. The closure of A is the set that's outside of A that is as close to A as possible, but just a little bit bigger that is closed. So in general, interior of A and closure of A are often very similar to each other, but not always. It can depend. Um, but one is sort of coming from the inside and growing up, and one is coming from the outside and shrinking down. Okay, interior of A, and closure of A. And they're always in this relationship that the interior of A is the smallest, it's contained in A, which is contained in the closure of A. All right, so that was a crash course on what interior and closure means. Thank you for listening.